Okay, so we're going to test the control. The volumes of testing for manual should be the same for automated systems, equal volume of plasma, same volume of APTT reagent, then we have an incubation that we'll talk about, and then recalcification, again an equal volume. On many automated systems, these are frequently 50 microliters, 50 microliters, 50 microliters, and that's acceptable. For manual testing, it's more convenient, 100 microliters of each of the three components. This gives us a bigger volume for visual observation that you'll see in a moment. So 100 microliters of control. So this now needs to come to temperature. It needs to come up to 37. We're performing this test in a glass tube, and glass is an efficient transfer of heat. So this will rather quickly, the small volume will quickly come up to temperature. So 1 to 2 minutes is acceptable. We need a fresh tip for each pipetting exercise. These are disposable pipette tips. If this sample is left for an extended period before testing, then there is the potential for change in the clotting factors present in the tube. So we don't want to leave these in at 37, 15, 20, 30 minutes. We need this to be in 1 to 2 minutes, come to temperature, make the test. At the moment, nothing's happening in the test tube. Simply warming up to temperature. But we're about to add the APTT reagent. So this has been warmed to 37. 0.1 of reagent. First tube, start the stopwatch and mix. Each addition, important to mix. APTT reagent, 0.1. The second of the duplicates, 15 seconds, and mix. So this contains activator, it contains phospholipid. At the moment, the activator, in this case silica, is beginning contact activation. So there are a series of reactions now occurring. This activation period has to be carefully controlled, carefully timed. Sometimes it's 2 minutes, sometimes it's 3 minutes, sometimes it's 10 minutes. It depends on the activator and reagent. This particular reagent is designed for a 3-minute activation. So we are carefully controlling 3 minutes. So during this time, contact activation, factor 12 converted to 12A. For this to happen, we need also to involve prekallikrein and high molecular weight kininogen. Those three are interacting on the surface, in this case silica, could have been kaolin, could have been ellagic acid, in this case silica. So these three factors are involved in this first process and interact in such a way that we get increasing activation of factor 12, more and more 12A. The longer we leave this activation, the more 12A is generated. And in a moment, when we add calcium, we'll run through the rest of the reactions. The 12A in turn activates factor 11. This is not yet calcium dependent. So we've got 12 to 12A, 11 to 11A occurring in this test tube just now. We'll add some calcium and we'll run through the remaining reactions leading, as you know, to fibrin generation. So longer activation, more 12A, more 11A. Shorter activation, less 12A, less 11A. Longer activation, 3 minutes, more generation. So we're paying careful attention to the stopwatch. Remember, we've got the calcium chloride, warming to 37. The autoanalyzer, of course, times this automatically. Working in the water bath, we have to do this visually. So we're now at 3 minutes. Same volume, 100 microliters, calcium to the first tube and mix. at 15 seconds, remember that we added activator, APTT reagent, 15 seconds later, exactly 15 seconds, second tube, and mix. So both tubes now contain calcium. The activation, the clotting process is proceeding, and we're tilting the test tubes, which we'll talk about in a moment, and we're looking at visual observation to look for a clot formation. Just going to record the clot and then we'll come back and talk a little bit more about this. The two clotting times we've obtained: 44 seconds, 44.4. So the first question, are the duplicates similar? Yes. Typically, we would see a difference here in a manual test at this kind of level, ideally less than 1 second, might be a second and a half, just could be up to 2 seconds, but we hope for that kind of precision where we've got very similar results. This is the control, normal control. So we want to know from this sample, for this QC material, which is the range that we expect? What's the target range of results? Is this inside our expected values? And for that we need to refer to the target range that's already been established for this particular control. And when we did this in the lab, this is done by repeatedly testing on different occasions the same control material. We obtained a range between 35 and 46 seconds. So that's our target range. So the first question we got, 44, is it inside that range? Yes. So we've established that the reagents and water bath is working as expected. How do we assign that target? Well, if we buy a commercial control, then the manufacturer will give an indication of the relevant target for their particular instrument and reagent combination. We know the results are influenced by the reagent, but in addition by the method of endpoint detection. So the manufacturer will give a target range. If we've made a control locally, as we did in this case, then of course we have to ourselves assign a target range. And there's a section in the WFH laboratory manual that describes in some detail how we would recommend doing this. It's done by testing aliquots of the control lot number, by testing aliquots on a series of different days, a series of different vials, and we accumulate 20 results over a period of at least 10 different days. And this allows us to take account of vial-to-vial variability, day-to-day variability, and we use that to construct a target range. And the target range we use is derived statistically. We use the mean value plus 2 standard deviations of the results as an upper limit, mean plus 2 standard deviations, and we use the mean minus 2 standard deviations as the lower limit. And again, this approach is described in the laboratory manual, so we'd refer you to that for the fine detail. Okay, so we have our control result. We're content that it's within the target. It means the water bath temperature is adequate. It means the reagents are behaving in the expected way. So we're able to proceed with patient tests. I'm going to set the next test running, and then I'm going to talk about the tilting of the tubes. So we've got a series of test samples. So number one is a sample from a patient. And we'll run an APTT with the same reagent on this sample. So once again, duplicate tests, 2 glass tubes. Fresh pipette tip. (100 microliters of patient sample into each of the 2 glass tubes. That's for the 2 replicates. I need to record the control value, 44. From earlier. So we've got the plasma present in the tubes. Simply coming up to temperature, coming up to the 37 degrees. Okay. So we're going to add APTT reagent to the first one and mix. Start the clock. And then at 15 seconds, APTT reagent to the second of the two duplicates. And mix. Activation, 12 to 12A, 11 to 11A. No further at the moment until we add the calcium. So whilst that's incubating, I mentioned the tilting of test tubes. There is a recommended method for tilting test tubes. It's defined by World Health Organization in relation, well, they define it in relation to testing of samples for control of anticoagulant therapy. And what their recommendation states is that the test tubes should be tilted 3 times every 5 seconds through an angle of 90 degrees. 3 times every 5 seconds. It sounds rather quick, but actually it's not. These 2 tubes are empty, but just to illustrate. 1, 2, 3. That's the kind of frequency. It's not this quick. And why is it that frequency? It's that frequency in order to balance 2 things. We want to keep the reaction mixture at the operating temperature as much as possible, 37 degrees. These reactions are temperature sensitive. If the temperature drops too much, the reactions are prolonged. So we want to keep the temperature. But if we're using visual observation, as we must do for a manual method, we also want to observe the clot when it occurs. So we've got this balance. And that's the 3 times every 5 seconds, is that each time we're up, we're looking. And as you see the next tilting, you'll see that the fluid is moving down the side of the tube and then back to the bottom. And we need the reagent in its bulk position in the bottom in order to observe when does the clot form. The majority of clots which form will be a fast process, will be a solid clot when it's a normal result, when it's a mild abnormality. It's fairly obvious with practice that the clot's formed. The longer the clotting time, the weaker the clot that occurs. So we're approaching the 3 minutes, so we'll add the calcium to this first patient sample whilst we're talking. So on 3 minutes, calcium to the first tube and mix. On 15 seconds, 3 minutes, 15 seconds, calcium to the second tube and mix. Calcium added, 11A from the contact phase, 11A plus calcium, 9 is activated, factor 10 is activated, prothrombin through to fibrin. So 3 times every 5 seconds through 90 degrees. Balancing the cooling as it's in the air with missing the clot as it forms. So I mentioned that the clot is weaker if the clotting time is longer. The greater the prolongation, the weaker is the endpoint. But of course, keep in mind, the longer the clotting time, the greater the abnormality, the less important 1 or 2 or 3 seconds becomes. If we're looking at a mild abnormality and we're asking the question, does this result sit within the normal range, or is it prolonged, 1 or 2 seconds could be the difference. And that's why in those first times, the early clotting, whilst we're observing, it's important not to miss a clot during that period as we're moving from normal to abnormal. But as we get more and more grossly prolonged, it's less important to be absolutely precise in the clotting time, which brings us, I think, to the reference range. Now, we need to record the clotting times. Remember, this is the first patient sample. So the first clotting time is 47 seconds. The second clotting time is 48 seconds. So we'll take an average.